Just going to wait another moment or two for everyone to get logged on. Great. So welcome to the Danish Sound Clusters webinar. Today, the subject is perceptual audio evaluation, and we have three excellent speakers today. Before we jump in, I'm just going to run a couple of polls to see who's with us today. So there are two questions. You might need to scroll down. And the first one is, where are you listening from today? Denmark, Europe, or the rest of the world? And the second one is, what is your background? The Danish Sound Cluster has been put in place to help the 500 audio companies in Denmark. But it seems from our last events that we're becoming increasingly international, but that's fine as well. Happy to help improve audio quality over the whole world. The last few people are just going to answer. Great. You can see the results. Actually, quite a lot from Denmark today. That's great. Okay, and a few practical things before we jump in. There is a regular chat for comments and general feedback, but if you have a question for one of our speakers, please use the Q&A chat instead, and then we will ask questions at the end of each talk. Don't use the raise hand function because you're too many people, so we can't keep track of it. So yeah, let's get started here. Nick Zacharov is our first speaker for today. He is the lead technologist at SenseLab at Force Technology. And he's going to give us a kind of broad overview and introduction to perceptual audio evaluation. So thank you very much for being here today, Nick.
Thanks a lot for inviting me.
Of course.
So welcome everybody. Hope you can all hear me. I'm going to try and share screen now, and let's hope that works. Okay, you able to see my slides now?
Yes, we are.
Super. Okay, so I'm going to give a short tutorial on modern sensory evaluation in audio, or perceptual evaluation. It is really going to be a high-level view of where the field has gotten to, and I think then the following speakers are going to give more application-oriented and the latest cutting-edge developments. So my one will be more tutorial in nature. Okay, so what are we talking about today when we talk about sensory and perceptual evaluation? It is this rather curious process of asking people to listen to sound and then give a score. And what can we do with that? We are still unable to measure directly our experience of audio by putting some electrodes on people's heads and getting a score 3.2 out. But we are, on the right-hand side, able to some degree simulate the auditory system and establish what we would perceive had we done a listening test. But we're going to be focusing on the big one there, where Homer's actually listening and scoring, which is may have been part of the input to some other studies which are going to be discussed today. Okay, so we're going to be talking about the applications to audio. So we're not going to be talking about perception of sound overall. So let's say sound scenes and environmental noise and so on, but focusing on the reproduction of sound, whether it's for hearing aids, headphones, or other applications. And all of these devices have quite a lot of electronics going on and transducers and so on. So there's a lot in play that leads to the audio quality that we experience. Okay, so when we want to evaluate quality, we need to understand what quality means. And the general concept that we talk about these days is quality of experience. And that's quite an interesting topic because it's been discussed for quite a long time what this really means. And quality of experience today is considered to be the degree of delight or annoyance of a person using a system. And with that comes lots of sort of additional understanding. There's a need to sort of fulfills one's expectations and needs, and there's an aspect of utility of the device in the situation. And when I say utility, it could be or enjoyment, depending on whether we're listening to speech for communication, or perhaps to music or a podcast for enjoyment. And all of that relates to the person's context and situation. So, of course, it's modulated by our mood, our experience, our personality, and also where we are. So are we in a quiet little office space like this, or are we sitting on a metro in a noisy situation? So all of that contributes to our overall experience. So quality sounds like a trivial thing, but in reality, when it comes to reproduced sound and audio, it's actually quite involved and complex. Okay, so how do we experience audio and audio quality, and how do we evaluate it? So I'm going to go back to a rather basic concept we've had for a few decades now, and talk about the way the brain processes things and how we can experience and evaluate audio, amongst other things. Okay, so here is a model which was developed by my colleague Torben Pedersen and his colleague Fo in about '98, and it's called the filter model. And the idea here is going from left to right, we have a physical sound, which basically acoustic pressure, and we can measure that with an instrument. We can take a microphone and we can evaluate that using whatever types of analyzers, and we can get physical measures. And those are very stable and reliable, but also they don't tell the whole story of how we experience things. Once we go into filter one, we talk about perceptual perception and the way these stimulus is perceived. And this is the first step. And it can be considered either in a very objective manner, where we think about characteristics such as loudness, where every single individual on the planet would agree. But there are lots of other sound characteristics which can be objectively evaluated by a human being. We then have the second filter, which is takes into account all of the subjective, opinionated aspects of an individual. And that leads to ratings related to affect or liking or preference. And this is very subjective in nature because what we each like differs, and it changes a lot with our situation, our mood, and all different other context things. The perceived stimulus, by comparison, is relatively stable. So as I say, we can evaluate things like loudness, and in general, people would tend to agree that we would all rank loudness in a similar manner. Okay, so how does it relate to other ways of looking at the brain? Well, Kahneman a few years back won a Nobel Prize looking at a two-system model of the way our brain works. And he talked about system one and a system two. The system one is a fast, parallel, automatic, effortless, slow learning process. And this is, I believe, related to the way we evaluate preference. If we think about how we choose things, we can take any type of product we want, whether it's two loudspeakers, and have a listen to them, and very quickly decide which one we prefer. We do the same thing when we try two different cups of coffee, which are maybe created in slightly different ways. We will instantaneously decide which one we prefer. By comparison, the system two is slow, serial, controlled, effort-filled, rule-governed, and flexible. So this is a bit more where we ponder things and decide why things are the way they are. And this relates quite well to the perceptual characterization, where we can evaluate that a sound has a lot of spaciousness, there's a lot of distortion, it's not very loud, and all of its other characteristics. And usually that takes quite a lot of time and learning, and is let's say, quite slow in nature. So as yet, it's not been proven that the Kahneman model is similar to or identical to the filter model, but there do seem to be quite a lot of relationships between the two. So this may be something for us to research further to confirm, but indicates that there is something likely to be found. So when we talk about the descriptive evaluation and effective evaluation, what do we mean here? When we talk about descriptive evaluations, we're talking about an objective quantification of the sensory strength of an individual attribute of some stimuli. So that means playing some sound to people and asking them to try and objectively quantify whether there is a lot of spaciousness, a little spaciousness, whether there is a lot of distortion or a little distortion. And doing this in a manner that people can agree upon across a population. But of course, to do that, we're talking about very technical matters. So we tend to use trained and expert assessors to do that. People who are familiarized with the terminology of, let's say, spaciousness and distortion and other such characteristics. And in doing this, we can actually perform quite an objective task, which is repeatable over time and over different types of panels. By comparison, when we think about effective evaluations, then these are very subjective in nature. And when we talk about subjectivity, we're talking about including individual opinion, which means there's a lot of variability because every individual has a different opinion, which may change from morning to evening or from different situations. So this is subjective and it's the basis of consumer studies. And that variability in the type of data is part of the process of effective evaluations. Okay, so to give you an example of this, I often show these several pictures. Here are two pictures. We can ask which one is brighter, and probably all of you would agree that the left-hand picture is brighter. You've understood the concept of brighter being the attribute, and you've looked at these pictures and evaluated, probably quite rightly, that the left-hand one is brighter. If we talk about an effective evaluation, it's looking at two pictures which are not too dissimilar and asking you which one you prefer. And probably there'll be a widespread of opinion whether you like the left or the right. And actually, we wouldn't even know what the distribution is from day to day. That may change, and you may change your opinion tomorrow. The left-hand side is likely to be stable over eternity, that everybody would score the left picture for which is brighter. So this is a visual analogy, and this is what we do. We do similar things with audio attributes to evaluate the nature and characteristics of sound quality. Okay, to dig a little bit deeper, I want to explain a little bit more about descriptive analysis in application to audio, and I'm going to talk about sound quality attributes. So we use the concept of sound quality attributes to, in a detailed manner, describe our perception. So we talk about things like pitch and loudness and roughness, and we use these types of words so that we can have a common language to describe what we're perceiving. And we're working towards building up what is called a lexicon, which is a standard set of terminology which can be used in a common manner across not only a panel, multiple panels, and maybe across an industry in due course. This type of lexicon is a long process to develop and has to be developed with many labs and so that we get a common understanding and agreement. And as I mentioned earlier, this is to be used primarily by expert assessors because, well, who really understands what envelopment means? And there's a lot of interpretation, even amongst audio engineers who work with these terms and listen to, let's say, audio systems that are enveloping in nature. So we're striving towards a common lexicon, and a lexicon really is a set of attributes which are well and explicitly defined, they're broadly applicable, and have a common basis for the evaluation of all types of sound systems. So lexicons are this standard set of terms which are used to describe sensory properties, whether they're for consumer products or otherwise. So to illustrate how this goes, how we develop a lexicon is typically this is done by an expert panel doing a lot of listening to a lot of different sound samples and coming up with terms that they believe would describe the nature of the stimuli being presented. And they come up with, first of all, an attribute name, and then based with that, to explain it further, they define that attribute, they define a scale with some polarity, so what is more and less, and ideally, to help the understanding, they also work towards finding a set of stimuli that illustrate what is a lot or a little of a certain attribute. So how far have we gone with this? Well, over the last few years, we've been working on what we call our sound wheel. This is for reproduced sound, and it has a lot of different sound quality characteristics. It doesn't cover everything in the field of audio, but it is a core set which we will find a value for evaluating loudspeakers, headphones, hearing aids, hearables, and lots of other different types of reproduction systems. It has several different areas and different layers. So the inner area are what we call attribute families, and the concept of timbre is to do with a sound color. So when we think about why does an oboe and a clarinet sound different, it is to do with timbre. They may be playing the same notes, but they have different sound quality characteristics, which are timbral in nature. Then we can think about the loudness, things up at the top here, and of course that's to do with the sound pressure level and how it's perceived. The dynamics are to do with how the quiet and the loud elements of a piece of music are experienced, and if there is a lot of dynamic or a little dynamic at high, low, and medium frequencies. Spatial sound characteristics are to do with where the sound is located. Are you being surrounded? Are the sounds very localizable and precise? Does the sound feel like it's inside your head or outside? And other types of characteristics. And then we have another quite important area, which is the artifacts. These are the undesirable things which may occur in a sound system, whether they are distortion or technical artifacts coming from other types of signal processing. So this is a basis that we've been using for quite a few years to train panels, expert panels around the world. And in addition to the wheel, for every single attribute, we have sound samples that illustrate a lot or a little of each attribute. So here is an example of brilliance with a definition and some illustrations of frequency response characteristics or otherwise that try to communicate the meaning of the attribute. Okay, so that's talking about the way we can use attributes to evaluate. But how about what type of panels should we be using and can we be using? So I'm going to talk about individuals, assessors, and panels here very shortly. So we all have a lot of opinions, and whether we're individuals buying a product, we have an opinion. But when we go into technical development, we see that managers have opinions, technical experts and developers have opinions, and then named golden ears also have opinions. And there can be quite a lot of tug of war, particularly in product development, associated with individual opinions. And that can be quite challenging. Now, one of the problems with opinions is that they vary over time. So on Monday, Tuesday, Wednesday, we may get different opinions from the same individual. So how do we make meaningful decisions, particularly in product development in companies that are going to be stable over time? So to avoid the mood, the expectation, the time, and just random variability, because all of this happens. So all opinions are valuable, but do they lead to good decisions? And this is one of the challenges. And it was something which I was challenged with going back about 15 years ago, where I was told that subjective testing is too variable. We can't make meaningful decisions in companies using that method. So how do we move from opinion to data, really? And this is where we start talking about panels, because by using panels of assessors, we start to get a stable population view. And this is data-driven. We then apply statistics to it, and we sort of try to remove ourselves from an individual opinion and the risk associated with it. While it is valuable, it is prone to variability. So what we're interested in is, instead of having one individual who on Monday, Tuesday, Wednesday could have a different opinion, we're trying to make sure that a panel, and it may not be the same panel, but a panel with the same demographic would yield the same data distribution on Monday, Tuesday, and Wednesday. If we can get to that point, and we can, then we are able to make decisions based on that type of data, and we can know that this is repeatable, and we can make good decisions based on it. So this is why we use panels instead of just one individual who, as I say, may change their opinion for whatever reason at a second testing. But what are panels? Well, there are whole loads of different panels, and depending on what we're trying to do, we may want to use different types of panels. So consumer panels are talked about, and consumer panels are representative of the normal consumer population. Of course, there are lots of subsets of that. So it could be that we randomly sample everybody in the world, and we say that that's the consumer population. Or we could think of subsets. It could be that we are talking about the normal consumer in Denmark or in the US or something like that. It could be the normal teenage population that we want to sample. So it is very important to know who are your consumers and to sample them correctly so that your data is representative of the group you are targeting. We also have, let's say, more expert groups of assessors, and I've mentioned them a few times. So expert assessors are typically normal hearing assessors who are extremely skilled at listening. They are typically trained in the field. They're interested in audio. We know that they're extremely reliable. We test that. They're very acute. They can hear things that, let's say, the average consumer may not be aware of. And they are not necessarily very representative of the average consumer. And sorry about the typo on the last line. That is meant to say not representative, not now representative. So the data that we will get from a consumer panel and from an expert panel is not equivalent. However, we do get fast data from an expert panel because of the nature of their the data they bring to a listening test. We also can consider other types of populations. So having a normal hearing expert panel is only useful to be representative of normal hearing assessors. But those of us who are over 50 and beyond may have some hearing loss. And today there are a lot of product categories, whether it's hearing aids, hearables, or even products that just want to try and enhance the experience for hearing impaired people are becoming more and more popular. Now, those products should not be really evaluated using normal hearing assessors, as that's not very representative. So we can also develop panels of hearing impaired assessors, and we at SenseLab have several different panels of hearing impaired assessors that are used for testing hearing aids and so forth. Okay, so once we have assessors, we need to know whether they're doing okay. We need to understand that they're bringing us meaningful data. So there are tools nowadays that allow us to evaluate the performance of assessors, to look at their discrimination skills, how repeatable they are, and whether a panel is in agreement. Discrimination skills indicate whether assessors are able to hear differences which we believe they should be able to hear. Repeatability is a measure of whether an assessor can give a similar score to a repeated presentation of the same audio sample. An agreement means, well, are the panelists in agreement and giving similar scores? The first two are the most important characteristics of expertise and a measure of reliability. Agreement is something that we watch to see whether there is a consensus across the panel or whether there are different views. I'm just going to skip on a few things here, but there are some characteristics of how assessors use scales which are acceptable, and then there are some which are unacceptable, which we evaluate on a constant basis. And using these tools, we're able to look at assessors' performance in terms of reliability and discrimination. And in a way, we can then find out who are the assessors that are bringing us good and valuable data to a listening test and which ones are bringing us noise. The crosshairs here illustrate the noise floor for discrimination and reliability. So the people up in the top right-hand corner here are expert or experienced in nature. People at the bottom left of the blue area now, the experienced ones, and the most expert are up going towards the top right. So here we have illustrations of some expert assessors in green, and we have some assessors who are performing quite badly in red down here and having particular characteristics. We can also see where assessors are starting to get over fatigued in the top right-hand corner when they've done too many listening tests in their career. So nowadays we have metrics that allow us to evaluate the performance of our panel very well. So how's the world developing in terms of testing protocols? And just going to go through things. So traditionally, we do tests in the lab, and this is still extremely popular. We take our codecs, we take all different types of spatial audio processing algorithms, and we test them in the lab in a standardized listening room with a standardized loudspeaker setup. Or we test headphones in audiometric booths, which are very nicely controlled. So this is still very popular. But today, things are shifting to more immersive testing, which are slightly more ecologically valid. So here we have several different examples of immersive sound systems with a lot of loudspeakers, maybe using higher order ambisonics or something like that. And we can actually take an assessor and put them into an immersive environment with a head-mounted display and switch between different noise scenes. This could be whether they be in a metro for one trial, and then in a park in another trial, and so on. So these people doing tests could be actually wearing a hearing aid or a hearable and go through different signal to noise ratio conditions and step through a number of different immersive scenes that are very accurately reproduced in the listening room. So this is a direction which we tend to be going in. And still maintaining the control of listening tests, and but also increasing the plausibility, increasing the ecological validity. We also do nowadays a bit more real world testing, and that means taking the product into the real world. The problem there is that whilst we're doing truly ecologically valid tests, there is the risk that we start to lose control of the nature of the stimuli we're testing in. So we could be changing the background noise level, and so testing the actual situation which we want to gather data from. So to do this, we do things called sound walks, whereby we know pretty well that if we drive a car around this block, we'll be driving at 40 kilometers an hour. The noise level will be approximately this. If we then head onto the highway, then there'll be a different speed, a different noise condition, and go through a number of different conditions which are interesting for testing the product category. Could be a walk in the forest, or walk along a busy street at a certain time of day, and trying to maintain those test conditions so that they are meaningful. Our software, SenseLab Online, allows us to go into the real world and do this, and we need to be very careful to make sure that the test conditions are stable when we're testing in such situations. I'm going to just wrap up with talking about test methodologies. Basically, when we do listening tests and perceptual evaluation, we are all the time fighting for the data signal to noise ratio. And we want to maintain as much, let's say, we want to be able to gain as much signal from the noise of a listening test. And this is all against the cost and effort of running a listening test. So it's always hard work. Now, in order to do a good perceptual evaluation or sensory evaluation, we have to pick a methodology from about 47 different methods. So there's a lot of methods out there to pick from, and we pick different methods to answer particular questions. So very shortly, I illustrate a few methods where we can evaluate different types of characteristics. So starting at the top, we can use things like the ABX test or triangle test to establish if there is a difference between stimuli. That may be the only answer you want, is are these identical or not? We can go through to things like standardized test methods like P835, which allow us to characterize the noise characteristics and the speech characteristics in a communication channel and evaluate the performance of noise suppression or active noise control technologies. If we go all the way down the list to things like consensus vocabulary profiling, we can use these types of techniques to characterize and describe the nature and the attributes associated with the products being tested. So with each of these steps down the list, the complexity of the test method increases and therefore the cost, but also the amount of information we can get from the method also increases. So I'd just like to say that today we have a plethora of different tools that answer different questions depending on what you are researching. So if you're interested in getting into this, do contact us, or if you want to get even more information, you can have a look at one of our 2 books. This is quite a fundamental book on perceptual audio evaluation from 2006. Still a lot of pertinent material in there, even given its age. And then more recently, we have updated the information with advanced methods, some of which I've mentioned here today, called sensory evaluation of sound. So with that, I will wrap up and thank you for your time and ask if you have any questions.
Thank you very much, Nick. That was great. Perhaps you could stop sharing your screen and we have a couple of questions here.
Absolutely.
Okay, from Dennis. Is it reliable to select the crowdsourcing service for the subjective listening test? What about the accuracy? And is there any guidance or methodology to organize and design specific crowdsourcing for a specific topic?
I think this is still fairly uncontrolled, and this is one of the major problems. You have no idea about, or quite often with crowdsourcing, you have no control of who is participating, what type of test setup they will be using. Will they be using loudspeakers, headphones? Will they be using good loudspeakers, or good headphones, or absolutely not good devices? So there's a lot of potential noise in crowdsourcing. When one reads articles about this, one sees that many tens of % of the data have to be thrown out. So the general practice is that you have to really post-screen your data and even put in, let's say, checks, which are quite important to catch people out and find people who are just are basically button clickers. So it's not a free lunch, the crowdsourcing. Now, I don't know if any of the other colleagues today will talk about this more, but I think that if you can pre-screen a panel where you have 100 or 1,000 people that you actually know their name and know their address type of thing, and you use them around the world, that will be a safer way to get started than just going total Wild West.
Yeah, you do have remote panels, right? You do have people sitting at home with their own setup, but you know what the setup is.
Yes.
Yes, so it's controlled. Excellent. Next, the E-gauge looks interesting. Where can I find more info on this? Can we play around with it? From Arijit.
Yes, so E-gauge is published in an ITUR report. It is called BS23, let me remember, 00. Let me just, I'll jump back to the slide, or I can put it in. Are we going to send out information after this, Shelley?
Yes, yes, we will share the slides.
Maybe if you take note, we'll share the slides. It is the reference is there, so you can search on the internet ITUR BS2300, and you will find the recommender or the report. And with that, there is some R code that can be downloaded.
Excellent. From Sebastian, what is your opinion about the model-based MOS predictor algorithm? Microsoft released DNS MOS P835. Can you see the question? Where they claim the predictor correlates with more than 90% with human subjective opinion. So panel versus model.
Yeah, I think this is always a question, and whilst models are getting better all the time, they do have finite applicability. So they were trained on a stimulus set, and it can be all shown that for that stimulus set, they do very well. The question is whether your new technology, which you're developing now, is going to be correctly predicted given the nature of the metric. And that's always a question mark. So that's evolving all the time, and that will move forward very fast in the next 5 years, 10 years. Jan has already been doing lots of good stuff related to that with machine learning. So I think we can see the trends there. You really have to know the applicability of the metric you are using. That will be the only lesson I would say. Some are very good for certain applications, but when you go beyond that scope, then they can be extremely unreliable as well. So know your tools as usual.
Great. And I have one question for you. Yeah, I know your sound wheel is available on the website, but are the audio examples available as well?
Not yet, and that's something we've been talking about, and I think there will be potentially an improvement in that direction in due course. So it would be highly desirable to make that step. And I would like to invite actually industry partners to participate in this. I would say in the audio industry, we are sort of doing this on our own and not pushing it, but bringing it forward. In the coffee industry, there are 20 partners who contribute constantly to the update of the coffee wheel. And that's something that we would need in the audio field as well, a collaboration on that topic.
There you go. Everyone's invited. Although I guess Nick will screen everyone who applies. Thanks a lot, Nick, for your presentation.
Thank you.
I think we will move on now to Jan. So Jan is, oh, we can't hear you, Jan. A moment. But Jan is a software engineer, manager, researcher, rock and roll musician. I'm not sure exactly what your official job title is, but
I don't know who put that together. I mean, yeah, I work at Google and I lead a research / product team. We're in between. We develop audio processing tools for conferencing meetings or YouTube. My team is called Chrome Media, so we're part of Chrome, actually. I'm not so completely used to Zoom, so let's see. How do I share a screen? Let's see.
There's a green button at the bottom.
Share screen.
Yes. And then you can select what you would like to share.
Let's see.
But thank you very much for being here today, Jan.
Yeah. So where can I see what you see? Can I?
No.
Nope. So do you see a title slide there?
I see a title slide, but I can also hear an echo of my own voice, and I can see your browser.
So
I'm gonna test
sorry about this. How do I do this? No, how do I share? Stop share. Because I want to play some sounds. How do I do that?
It is possible. There's an option to share sound as well when you press.
Yeah, but then you get echo, right? So then I have to mute when I play. Okay, that I can do that. But so don't share.
When you share, there's a little arrow under the share, which allows you to then select whether you share sound or not.
Yep. Let's see. So now
Yes.
if I pick this window, is it shared? But
it is.
But you also see my browser.
Yeah. If you make it a full screen, can you do that?
Okay, and stop share again then, or where? Where do I set this?
Whenever you decide on what you want to share.
But desktop. And
desktop will share everything on your computer.
Okay.
And so if you select just the PowerPoint presentation.
Let's see if I do this and I do full screen.
Then we can see your presenter view.
Okay, let's do it again. I have to share the entire screen unfortunately, right?
It's no problem.
Yeah. I'm not allowed to use Zoom because my company feels that it's not safe.
Yeah.
So,
okay. Well, thanks for.
This is my private laptop. So desktop share and
yes. Perfect. Yeah.
Okay. So if I want to share, okay, let's take that when we get there. Do you get an echo?
No.
Okay.
I do not.
Okay. Okay. So sorry guys. Yeah, and I'm a novice here on this technology. What I'm going to talk about is actually on the lower end of the quality scale, because Nick talked more like on the even up on the high end with spatial sound and all these nice loudspeaker and all that. I'm going to talk more about the kind of pure core speech communication that can happen. And recently there have been advances in, as Nick said, machine learning and neural networks, and we can use them for both the compression and also for assessing quality. Today, I'm not going to talk so much about assessing quality using AI, more the compression technology for low bitrate speech coding. And first of all, what is speech coding? It's basically compression of speech, data compression, because it's all digital. You take input speech, you extract some features, like parameters from speech, and put them into a digital format. You quantize them, send them over a channel or store them on a disk. And then you do the reverse thing on the receiving end. And in the end, you just use these parameters to drive some speech synthesis. And you can question now, because everyone has high bandwidth now, and everyone has using lots of video streaming and all that. Is there actually a need for, is there a communication problem? Do we need really low bitrate for speech? I used to work in speech coding 20 years ago when cellular telephony was kind of the thing, and secure communication, very low bitrate. So what today, do we really need this? Go down into like kilobits of kilobits per second range. And it is actually still a problem. There are, the infrastructure in the world is, for data is extremely diverse. There are people, mobile subscribers with data plans that are actually not on data plans. They're still using 2G networks, doing communication over data networks. So it's not cellular telephony. These are actually voice over IP or internet telephony. They're using 2G networks, and 1.5 billion more and counting are still on 3G networks. So that's pretty low data rates. And another thing is, I don't know about you, but here in the US and also around the world, there are these unlimited data plans. And if you download too many YouTube videos, your operator will just throttle the bandwidth after a while because it's not unlimited. And then in the end, you have 64 kilobits per second or something slow for the rest of the month. And then you're also out left in the cold. And the last couple of years, especially the last year, people have been more working from diverse locations, such as home or wherever you sit during these times. And that has highlighted, especially I can tell you here in San Francisco, even though I have really high bandwidth nominally, there could be spotty network connections. You're sitting on a bridge and there is a traffic jam. You can get really spotty network connections. So occasionally, even though we have nice phones and nice data plans, the data networks will go down and you will need low bit rates. Okay, so what then if we're gonna try to be a little scientific here, how low can we go in bit rate and still have a useful communication? And this is something that people have been playing around with since data communication started for not that long ago, 50s, it's 80 years ago. Shannon was one of the most well-known. He estimated using only English language and the frequency of words in English and the talking rate normal people have. he approximated or estimated that you can go ahead with only 50 bits per second to convey input speech and the fidelity, so that the output speech will be intelligible. And that is kind of that you take the input speech, you do the best speech recognition you can do, so just convert all the audio into text, and you send that text over with some information about like emotions and prosody, that's intonation, and who's speaking and all of that. If you take all that information, you can compress that pretty hard. And then in the other side, you do the opposite. So again, you take text-to-speech synthesizer, the best speech synthesizer you have, and produce output speech. When you do that, you can get down to 50 or 100, around 100 bits per second. And that was also confirmed recently when there was a more scientific approach on actual regular speech, several languages, around 100 bits per second. So why don't we use that? Well, these are theoretical limits, and of course, it's hard to get to those. The main obstacle here is, even for Shannon, that you really have long delay in order to get there. In Shannon's case, you need infinite delay, and that's kind of impractical. So in practice, what kind of bit rates do we use, and what types of coders are out there? The family called Parametric Coders or vocoders, they can go very low. They can approach these lower limits. Because they are based on a speech model, where you have a model that for different sounds, and you extract parameters for these sounds and drive a speech synthesizer on the other side. So this is very close to what in the previous slide. That the problem with these coders, even though they can go very low, as around 300 bits per second, they are completely limited from the model. It doesn't matter how many bits you throw at it, because in the end, even if you don't quantize or with the infinite bit rate, you can't be better than the speech model. So you see here the green curve. If you increase the bit rate, it will just flatline. So, and these traditionally are not very high quality either. So they are mostly used and limited to narrowband speech for secure communication. So it's 8 kilohertz sampling, and they're used around 5 to 4 kilobits per second. The other big class of coders are the waveform matching coders. They are not trying to model the sound, they are trying to mimic the waveform with increasing fidelity. The good thing with that is that the more bits you throw to it, the more you get closer to the waveform, and in the end, you will get, if you have infinite bit rate, you can get infinite fidelity, you can get perfect reconstruction. The problem with these is that when you go down in bandwidth or band in bit rate, they will collapse and break down. So there are use cases for both of them. The waveform codecs are much more deployed because they can use higher bandwidth, and they can do stereo. So they are used for many applications. So for voice conference or video conferencing, for that matter, or internet telephony, up around now, or up till, let's say, until 2017, this was the scene that internet calls, that's conferencing, like what we're using now. Right now, I'm pretty sure we're using a codec called Opus, and it's running at 32 kilobits per second, a wideband coder. And these codecs are very often, they are waveform matching coders. So if you want to go down in bit rates, let's say that Zoom feels like, oh, the channel is really bad, we need to go down in bit rate, the codec, in this case Opus, will break down around 5 kilobits per second. So if we want to go lower than 5 kilobits per second, what can we use then? Yeah, we can use these parametric coders, these vocoders, these old school ones. The problem then, of course, we have to trade off that we will have robotic sound from this speech synthesis models used in this old codecs. So the question we said to ourselves around, yeah, 2017, that's why I put that number in there, or that year, because that's when the new models for speech synthesis started emerging. So can we do better parametric coding? Since they're using parametric coders use synthesis models. And around then, AI, or neural networks, or deep learning, or machine learning, all these names, fancy names for these advanced neural networks, they started flourishing around this time. The first one that was got attention in the world was the WaveNet system from DeepMind, a group in London. They came out with a system called WaveNet that generated speech from just a pure model, network model, a huge one though. But the thing with what's really astounding and remarkably high quality of the speech that it produced. And I have to admit that I haven't heard anything, or still haven't heard anything that sounds as good as the first WaveNet. The problem is that it had really high complexity. It was absurd at the time, 100 plus megaflops. So it has to be like a data center or to produce speech. And that's okay if you do cloud computing. So WaveNet had its uses, and it's still used. No, it isn't used actually. The basic first version of WaveNet was just research. So we thought that we can use that. We can try to exploit these new models. The thing is that text to speech, where you write a text and you derive rules for how to pronounce it, and then you drive the synthesizer, it's a bit different than parametric speech coding. The features that you use in text to speech could be the same. It could drive a speech synthesizer with their vocoder parameters, but these features are generated from real speech. They are extracted from real speech and in coding, whereas in text to speech they are rule based, and so it's slightly different, but not so far. No, I mean that's not so hard. It's just do a proper speech analysis. The thing that we were a little bit uncertain was that in text to speech you typically have one or maybe a few speakers that you've trained, and you know them in advance. So you have a system that's really good for a few voices. In coding, we want to use all speakers, or anyone should be able to speak in the speech coder. So you need unseen speakers. So that's kind of the reason why we did this experiment. We took we wanted to do a WaveNet driven by different voices. And that first experiment we did was actually pretty good, or not good in the sense that, yeah, good in the sense that the outcome was good. So what we did, we took a codec or a coder that open source coder we found called Codec 2. It's a good thing is, I mean, it was open source, so we can play around with it. And we used the encoder from this. We took analysis and from this and quantizers. So we just used the encoder side. Then we drove a WaveNet with these parameters to condition the WaveNet and generate the speech. And we got pretty good results at 2.4 kilobits per second. We did some listening tests. That's what we have to do, because otherwise we don't know exactly how good it is. And this was a closed test within company, and we had 20 participants. We compared the original with a couple of other codecs. Some parametric coder down in that range that we were interested in. Codec 2, the one that we used. Also MELP, which is a federal standard. And we had, as an anchor, we used a really poor codec called Speaks. It's not poor general, but in these low bit rates, it was really poor. And we can just look at the results here. So the codec 2 and our wavenet coder are the same encoder, but different decoders. And you see here that the results show that it sounds really much better, almost approaching codecs that are almost 10 times in bitrate. But we should listen, I think. And now I need some advice again. What should I press?
Are your audio samples in the PowerPoint presentation?
Yep.
So perhaps if you click on that, let's see if we can hear it.
You can't? Do you hear anything?
Nope.
No. So.
When you share screen, you have to select the share audio option. That's the trick.
Okay.
There's a little tick box, yeah.
So the bottom left corner, when you're in the share screen, it says share sound in the bottom left.
Yes, now yeah, but then you can get some echo, I guess. So I need to mute somehow, right? Share.
Under terms previously reported, the
We can hear
Italian
it.
agricultural concern assumed
Okay.
about $195 million
good.
in subordinated debt as part of the transaction.
So this is the original sound. And now I use the codec 2, that low bitrate coder that we used that we took from internet. And this is how this vocoder sound at 2.4.
Under terms previously reported, the Italian agricultural concern assumed about $195 million in subordinated debt as part of the transaction.
And then using the same encoder, but driving a big wavenet synthesizer, you get this quality.
Under terms previously reported, the Italian agricultural concern assumed about $195 million in subordinated debt as part of the transaction.
I can hear this, but Mess says that they cannot. Can everyone else in the audience hear them? Okay.
Okay.
Yes, they can hear.
Okay. And you should, let's play this again. This is the 2.41. This is the one that. Okay.
Under terms.
Again. I don't know why it doesn't show that it's playing.
Previously reported, the Italian agricultural concern assumed about $195 million in subordinated debt as part of the transaction.
This is, I can compare this with a high bitrate AMR wideband codec that is almost 10 times.
Under terms previously reported, the Italian agricultural concern assumed about $195 million in subordinated debt
you get the drift.
as part of the transaction.
We can do really well. And these neural systems, these generative synthesis that we used here in this example, they are really good in modeling and generating a single source of audio. In this case, speech. WaveNet has also been used for instruments like piano, saxophone. So they are really good in one single source. However, if we want to try to do like general audio or general things, types of sounds, it doesn't go so well. I have here example of when the WaveNet coder tries to code music. And I hope this is the original music. Okay, so this synthesizer can do only speech sounds. It's really good in making speech sound. Now it listens to music and tries the best with the speech source it has. So that, of course, is a problem. But this was a research project, and since then we've tried to cope with all types of sounds. And nowadays we are a little bit better, but then again, we can't get these low bit rates either. So there's a trade-off. But this was just an example of showing what can be done by this generative synthesis. When you develop coders like this, or when you're in this business of processing, you want to have an objective metric. Nick talked about that too, and also in the questions before. It's always good to have something simple that you can just run your audio clip on and get a number. And sometimes they are good for certain, as Nick said, they're designed for a certain thing. Here comes a new technology that is not at all similar to previous technologies. So according to Polka, which is a respectable, and also you have to pay a lot of money for it, it's a metric for speech quality, where you compare an original to a processed one. According to Polka, our WaveNet coder that you just listened to, it is as good as Codec 2 and MELP as we heard it wasn't. I mean, Codec 2 is a robotic narrowband one, and our WaveNet one was crisp and clear, although it just produced speech sounds. But here is speech in this table here is just for clean speech, so it should predict well. It doesn't, and none of the conventional quality metrics are useful. The reason is that these generative systems, they are modeling a probability density function of the speech. So every time you make a sound, you draw a random sample from this density function. So the output is a likely waveform, not exactly the signal that you put in. So these metrics can't really figure out that similarity. And so that means that we really need to continue using human subjective tests. And as someone else asked too about like crowdsourcing, we have people like Nick and his team. These are really good assets if you want to do a real accurate test, especially if there's just a small differences. It's great that we have facilities that can test that very accurately and get good results. Unfortunately, it's a little bit time consuming, it's expensive. So if in the developing phase, you don't want to do that too often. And we still need to do subjective tests, because we saw there are no good objective tests, although we're working on it. But right now, when we're developing these codecs, we need to have some kind of assessment system. And we can do listening tests ourselves, or panels of expert listeners. Again, it takes some time. So luckily, there is this alternative crowdsourcing. And we use that a lot, because you can concentrate on doing other things, then you do crowdsourcing tests, and then you get result in 2 days, and then you continue. So it's a good way. Normally we have objective tests that are not so useful, but sometimes they are. and then we do crowdsourcing, and then we do real ones. So it's good to have that arsenal of different tests. And when we do crowdsourcing, we typically have a panel. These are paid by Google, so it's a panel, but there are lots of them, and we use the same group all the time. Typically, we have around 100 ratings per processed clip, and it doesn't have to be. Each rater has do a subset of the clips, so we don't have the same raters for all the clips and so on. And the only conditions we have is that they have to use headphones. So these people can sit. They do sit in the U.S. though. There are U.S. native English speakers, and they sit in the U.S. But we don't know what equipment they have. They have headphones, and that's it. And we need to do post screening because we've been doing this for a couple of years now, and we've also compared the results from crowdsourcing compared to what we do in-house. And so here's a result of a test we did within my team. So we're 7 listeners. I think Nick can actually confirm that we are expert listeners, some of us, because I did his course and got a diploma. So we are expert listeners, and when we compared our results with the crowdsourced, we see that the trend is the same, and the general kind of individual ranking is the same. But the naive listeners, for instance, they're pretty poor in finding the reference compared to expert listeners. But you see, there is value to it. You have to know that we can't really get the absolute values, but we get ranking pretty well if you use enough listeners. So that's kind of assertive for us, so that we can get certain for that. But and again, if we want to be more, and especially if the clips are too close to listen to, we have to listen ourselves. And but also we need a good objective metric during development. I feel like, especially when you train these systems, during training the neural models, we can't only take the losses that we have in the neural networks. We need to produce some audio and get some sense of fidelity. And so we have worked with universities in the past to develop assessment. One successful one was called Viscol, and with the same people in Dublin, we last year we tried to address these generative systems. And the main thing with these AI-based ones is that when they generate audio, it will not be time aligned. It will be time stretched or time compressed. There's no sense of synchronicity between the input and the output. So what typically is done in old school signal processing is what's called dynamic time warping. So we simply did a test on that. Take a similarity metric, but use time warping to synchronize and align segments of systems. So you take the speech, you go to a domain, in this case, Mel-Kepstrel coefficients that are normalized. We do that for both the input and the output, the reference and the degraded one. You take a small patch, I can show you in the next picture. You take the reference signal and you take the, in this case, the wavenet signal. You take a patch and you sweep it and try to find where they are most similar. And after that, you try to get the minimum for each patch, each position, and you gradually go through the file doing this and get an optimal path and get a score. And this works very well, actually, both for regular systems and for these new ones. And here we call it warp Q. And you can see this is the correlation, or here's a scatter plot here to the left from the all the points in the for the listening tests and the predicted output from the warp score. And you can see there is pretty good correlation. It's a negative correlation, but yet it's still somewhat a straight line. And we also tried, so in the middle there are different type of synthesis and codecs, some traditional ones. The red ones are regular traditional codecs, and all the green ones are these neural generative synthesis of all kinds. And so these codecs were all in, not these not this exact ones, but these type of codecs were in the training set for this metric. But the rightmost one are, if we just take a completely new set of codecs, and we still get pretty good correlation. So this still working on trying to improve this metric. Summarize, these systems are really impressive for a specific source. So we can go very low in bitrate if we know that we have one single type of source, speech in this case. We have to do a little bit more to get like noise robust and other types of signals, but it's really good for low bitrate speech coding. However, we need to have new objective metrics. Otherwise, we are bound to use subjective listening tests. And that concludes my talk. I guess we have time for questions.
Thank you very much, Jan. I can hear my own voice.
Oops, now I have to stop sharing again then.
Yeah. Thank you very much. We actually don't have very much time for questions at the moment. Would you mind if we continue to Charlotte's talk, and then we can come back?
Sure.
At the end for those people who want to hang around for a bit longer. There's one thing I've learned since coming to Denmark. It's that the Danes are a punctual bunch. And yeah, I think we should move on to the last talk for now. But if you have any questions for Jan, you can write them in the Q&A and we'll come back. Charlotte, welcome.
Yes, thank you.
Charlotte works for GN Hearing, and she, we have here. Yes, she will do the final talk for today. So thanks very much for being here, Charlotte.
Thank you very much.
And we can see your presentation. That's great.
Super. And today I'll be presenting more, if we already been a bit through this topic with Nick and Jan, so that's nice, on objective metrics for perceptual audio evaluation. And this is a broad overview on what you need to know, what they are, and for using them. So if my cursor works, there we go. So we covered the traditional use using subjective listening tests with human listeners, and with objective metrics, what we really want is to be able to have an objective metric that could reflect the performance of the human listener, of the auditory system and brain, to get some sort of perceptual rating. So looking at the definition, it's a mathematical formula that at least attempt to predict how human listeners would perform or rate the audio signal. Traditionally, when we think of perceptual audio evaluation, we think of quality and different aspects of quality, but it can be many different aspects in this perceptual metrics. So other is intelligibility we often look into as well, but also listening effort or loudness perception, speaker identity, or emotional state. And now we had Jens talk on AI, and it makes it more complex where stuff like emotional state and speaker identity is relevant to consider as well when we reconstruct the signal rather than use filtering approaches. So really any perceptual aspect you would like to quantify, you could use an objective metric. For this talk, I'll focus on quality and intelligibility metrics. So we already discussed this a bit. Should we use the subjective or objective evaluations? And the advantage of the subjective tests is clearly that it reflects the actual performance or quality judgments of the users. So it's more trustworthy. But it's also time consuming, expensive, and we're not able to do this during real-time processing, or at least not very feasible. And for the objective metrics, it's a fast, cheap, and can be applied for real time, at least for some metrics, and high reproducibility. However, the usefulness is also constrained by the reliability, as we already have discussed a bit today. So what should we use of this? And actually, we should use both. So during development where we would like to have fast results, it can be smart to use the objective metrics and use them during optimization of algorithms, and also to do large grid searches of different parameters. But at the end, when we want to evaluate our results, we should really use subjective listening tests as well to make sure that what we find with our objective metrics concurs with subjective results. Then objective metrics can generally be divided into two classes: intrusive metrics and non-intrusive metrics. The intrusive metrics are the most common ones, also called multi-channel ended or two-channel ended, where you both have a clean signal and a noisy signal. So it's a bit of a theoretical signal. You can't record it out in the environment where you already have the noisy signal, but it's very useful during development where you can generate signals yourself. Whereas non-intrusive metrics is where you only have the noisy signal and not a clean speech signal available. For example, in my domain with hearing aids, we most often only have the noisy signal available on the hearing aid. And I'll get back to more about this later when discussing some different metrics. Yeah. And for example, here, which could be very relevant, improving the strength of metrics over subjective scores, is that if we have a fast and robust online evaluation, then we could also adjust processing live, for example, on the mobile phone or hearing devices or during the Teams call. So dynamically, we could have the processing estimate the metric here. It's specifically mentioned intelligibility, but it could be anything, quality, and so on, and adjust the processing to the output to the listener. So metric goals, what we want is really a universal model. It should be able to generalize to all listeners and processing conditions, so it's reliable also for AI or codecs and so on, what have been mentioned. So it's really important to discuss and consider what should the metric account for, types of processing, acoustic environment, speech material, hearing loss, and so on. However, metrics depend on the training data, if it's a data-driven model, or assumptions of the model for parametric models. So we typically have it divided into white box models, parametric models that's developed on knowledge of, for example, the auditory system and how it's built up, whereas black box models or data-driven models is more based on fitting current data to the model. And often we work in the in-between, in the gray box area where we have some prior knowledge. sorry, I just had a phone call interrupting. So for both, they are dependent on what data they have been trained for. So for the parametric model, you would directly think how the model should account for the specific data and develop the model for it. Whereas for the data-driven model, you are fitting data to the current data you have, and that limits the performance. So often you would generate predictions, try to compare it with your system output, and then update the model to it. So in some of the cases, we have current models where we had it fitted to the model, but getting new predictions so it doesn't fit. And therefore it's important to investigate which models work for what and update them as we get more knowledge and different processing types we need to account for. So how do we get accurate predictions using these metrics? And here it's really important that you need to develop and train and validate the metrics and similar processing types as you want to measure it on. So if you have a metric that's only been developed for linear processing and only validated for linear processing, you most likely can't use it for non-linear processing types or AI processing types. So it's really important to know the functioning area and limitations of the metric you are looking at. Then here also an important point, often overlooked, is metric values should be average over stimuli to reduce the variance and sampling bias. So you can't just run a metric on one single audio signal and say that's the score. Like for subjective listeners, you need to run it over a multiple of different sentences and take an average across all these scores because you would have differences between each sentence, how it is, but some metrics also have internal noise in the metric. So to not have a sampling bias for the signal you're looking at, you need to run it over a multiple of stimuli and take an average. Then metric values need to be mapped into subjective ratings using psychometric functions here, as we see in the figure, where you have for the short time objective intelligibility metric STOI versus intelligibility. You can't straightly take a score of 0.6 and think it corresponds to 60% intelligibility. You need to know the mapping between the scores and the perceptual subjective scores you are looking at. And it's quite important to have in mind what the different scores actually mean. And also using the clean signal as reference in the intrusive metrics does not necessarily correspond to the best performance. And this can seem counterintuitive, but often if you can't do complete processing, human listeners prefer a bit of internal noise. So using the clean signal as reference and comparing the process signal with this can often give a mistake, and this is especially evident in AI types of processing. I'll get back to this with an example later on. So for objective perceptual intelligibility metrics, intelligibility is a measure of how much of the speech is correctly identified. And there are some examples of the most common intelligibility metrics, the SII, STOI, HASP, EPSM, SIRMI. And for a talk like this, I don't think it makes much sense to go into all the metrics that exist out there or go into every single one of them, because there is really many and it really depends on what you want to use them for. So I'd rather put emphasis on that and look at evaluation of the metrics in general. So here's a huge amount of data, but just to point to that this is the way to go to figure out what metrics should be used for different situations, is finding different reviews here by Van Koek in 2018, a huge review looking across a lot of different intelligibility metrics and related to different corpuses and a lot of different processing types. So for example, HASP and SIBB correlates highly across a really wide range of types. So you would point in direction at looking at these and look at data. How well does it correlate with the data I'm looking at and want to process? So tables like this can be very useful for what do I need of model parameters, and what environmental degradations do I have, types of noise and reverberation and so on. What type of processing effects do I have in my signal, and look at which models are useful in which situations, and which ones should I use. Because as models are today, we don't have one single model that can be useful in all situations. So it has to be a careful choice of what objective metric to use in which situation. And this is all intrusive metrics, whereas for the non-intrusive, it's a much newer area. So as you can see with the question marks, it's highly lacking data for evaluating all these metrics at this point, and also less developed to account for broader ranges of data here for intelligibility metrics. Looking into perceptual quality metrics, where quality is a measure of the naturalness, clarity, and distortion of the audio signal. And some metrics looks at different attributes of quality, but most looks at an overall quality score. So some of the most common is PESC, HASCII, and Polka, VSCOL, and PS, but this is just for mentioning a few. Again, there's a lot of different metrics, and I'll not go into details how every single one of them works and what situations. But again, point here at a review by, oh damn, I missed the reference here, but it's Tocoli, I think his name is Matteo, a recent review here from 2021, comparing a wide range of metrics, and also considering this with different domains, with the source separation domain and audio coding domain, to see that you should have a high score correlation here of 1 with subjective data in both domains to get this metric working well in both. And here he proposes a new model, the 2F model, having a really high score for both source separation and audio coding, but also still PESC and HASCII, that's James Cates HASCII, different models performing relatively well. So here another review by Müller back from 2011, where you have tables with recommended uses and limitations. And here I would say limitations are not just the one listed here, but everything where you can't find data for the uses of them, you should be careful and at least do some subjective tests to compare with as well. So here are some examples of using training data. Here is the hearing aid speech perception index. It's an intrusive intelligibility metric that's based on an auditory model, coherence-based, but also have some training data in it and has a small neural network. So for the first version of FastB, it was trained on noise and nonlinear data, and some frequency compression and ideal binary masking, noise suppression, aimed at hearing impaired, so hearing aids. And we can see for what it was trained for noise and distortion, you have a very nice linear correlation. But for reverberation, it doesn't follow very well. Adding the training data in version 2, we get a high correlation for reverberation as well, with having the reverberation included in the model. So it's a way of being able to update the models and remember to include when we get new processing types emerging in our signal processing world, we need to update the metrics as well so they function for the areas we're looking at. Another example is here a study by Lee, also recent 2021, with post-processing increasing MOS scores. So he proposes the algorithm TSCN. I won't go into details what it is, but a neural network-based method showing that from noisy to this method, it increases PESC and ESTOI scores. So ESTOI is also an intelligibility metric, PESC quality metric. I'll focus here on PESC because they looked at MOS scores. But if you look at the MOS, you do see an improvement from noisy to the model. But here the PP, the post-processed one, where you add a bit of noise, increases even more. And often for the AI processing types of networks, having the clean as the ideal, you often would make it too good. So the artifacts will actually degrade the quality. You would have little left. So adding a little bit of noise can make it more salient, but the metrics favor the clean representation. So it's often here in the small details. They will fail with these more filtering-based AI approaches. So it's a way of looking into where do the metrics fail, what do we need to do to update them and make sure they work in these areas as well of signal processing. So to conclude on it, it's important to choose the right metric. The accurate metric results require that the model have been trained or modeled using similar signal processing types. And you need to be careful how you use it. The value should be averaged across different stimuli to reduce variance and sampling bias, and follow descriptions on how you should use the metric from the developers of the metric. And you should be careful how you interpret it. Metric values need to be mapped into subjective ratings. You can't just directly say anything from the metric score in itself. It varies with what speech material you use and acoustic background. So score, for example, of the STOI of 0.6 for one sentence and 0.6 in another sentence might not be the same subjective score. It depends on the data set and the speech material you're looking at. Thank you. And any questions if we have time for them?
Thank you very much, Charlotte. Oh, can you hear me?
Yes.
Yes. I think if you stop, sharing your screen, that's great. I have one question, and that is there one place where we can read about all of these metrics, or apart from, or maybe it's just your PhD, is that where we go to if you want to learn more?
Yeah, so some of the tables are from my PhD, from at least the intelligibility area, but otherwise I would refer to some of these reviews I'm mentioning here in my talk.
Great.
It's mainly reviews collecting and comparing over wide ranges of data.
Perhaps if those links aren't in your presentation, we could also share those with people today.
We can do that.
That would be great. Nick and Jan, do you have any questions? Then we have one from Laz Bumslow. Are you concerned with loudness? In hearing aid applications, quality is not relevant if loudness is bad.
It depends on what you're doing and the application. And it's definitely something that is nice to take care of and look into as well. We have some situations where it can be and some where it can't. But for example, introducing AI, it can sometimes be more unpredictable what the metric is doing, depending on what type it is. So that would also be something that's important to consider.
Thank you.
I would actually have one question if there's time.
There's time.
So thanks a lot, Charlotte. I think it's a really nice overview, and there's a lot happening in this field which we all have to keep our eye on. One thing which did catch my eye is you talked about a model which would be unified for many, many things, and you talked about for all different types of, let's say, users. Is your view that that's the sort of holy grail direction that we should be striving for, or do you think it's something that we could sort of pragmatically achieve or not?
It's at least what the community is striving for at this point. Question is if it's realistic, because adding a lot of different training data also makes it less precise across all if you want to perform really well in one situation, or a little worse across many situations. But from a usage perspective, looking at papers, you can really see how much the metrics are misused. So people, without thinking if they're applicable for their area or not, using STOI or PESC or Polka and so on for everything without considering if it even makes sense to use that metric. So even if it comes at a little cost of performance, I think the holy grail metric would be to prefer, rather than making this metric, use this for codecs, use this metric for AI and so on. I think it'll be very chaotic. It is already chaotic with the amount of metrics out there. But it's a trade-off. And we also see it a bit with our standardization process. We have a lot of standardized metrics, which is very good that we do this process, but it's also heavy and time consuming. So they're not necessarily up to date or the best or reflecting what we need right now, signal processing wise, and what's being done. Yeah.
Thanks.
Great. If there are no more questions for today, then I think we should wrap it up. I see that Jan and Nick have answered some in the chat. So thank you very much to all of you for being here today. It's really interesting, and I'm sure that we have a lot of participants who find it very useful. And this recording will go on the website. We're going to send the presentations, and yeah, we hope to see people again for another event. Most of the time it's in English, and it's always free to attend. So hope to see you soon. Please take a minute to fill out the questionnaire. That will really help us improve the work we're doing in the cluster. And for those of you who haven't already, for those of you in Denmark, we have an event called Danish Sound Day on the 17th of November at Aalborg University in Copenhagen. So you're very welcome to see us there in person, and that'll be great after all of these online events. Thanks a lot for coming, and see you soon.
Thanks.
Thanks.
Bye.
Bye.
Thank you. Bye-bye.